Quantum computing represents a fundamental shift in how we process information. It moves beyond the limitations of classical computers that have defined the digital age. This new paradigm promises to tackle problems currently considered impossible. This technology is poised to revolutionize numerous fields. Areas like medicine, materials science, finance, and artificial intelligence stand to benefit immensely. The potential impact is truly transformative across industries. At its core, quantum computing leverages the strange and powerful principles of quantum mechanics. These are the rules that govern the universe at its most fundamental level, dealing with particles and energy. It's a world far removed from our everyday experience. Instead of using classical bits, which can only represent a 0 or a 1, quantum computers use qubits. These quantum bits are the basic unit of information in this new computing model. They behave in ways that classical bits simply cannot. One key property of qubits is superposition. A qubit can exist in a state that is a combination of both 0 and 1 simultaneously. This allows a quantum computer to represent and process vastly more information than a classical computer with the same number of bits. Another crucial quantum phenomenon exploited is entanglement. When qubits are entangled, their states become linked, regardless of the physical distance between them. Measuring the state of one entangled qubit instantly tells you the state of the other. These quantum properties, superposition and entanglement, enable quantum computers to perform complex calculations in ways that are fundamentally different from classical machines. They can explore many possibilities at once. This parallel processing capability is inherent to their design. This allows quantum computers, even in their current early stages, to exceed the capabilities of the most powerful supercomputers for certain types of problems. While not a replacement for classical computers for all tasks, they offer a unique advantage for specific computational challenges. The field of quantum computing is seeing steady breakthroughs that are continually pushing the boundaries of what's possible. Researchers and engineers are making significant progress globally. The pace of innovation is accelerating. Major strides are being made in building more stable quantum processors. Qubits are incredibly delicate and easily disturbed by their environment. Improving their stability is crucial for reliable computation. Simultaneously, significant effort is focused on making quantum processors more scalable. Current quantum computers have a limited number of qubits. Scaling up to hundreds or thousands of high-quality qubits is a major engineering challenge. Error correction is perhaps the most significant focus area in current quantum computing research. Qubits are highly susceptible to noise from their surroundings. Even tiny vibrations or temperature fluctuations can disrupt their state. This susceptibility leads to decoherence, which is the loss of the quantum information stored in the qubits. Maintaining the quantum state for long enough to perform complex calculations is extremely difficult. Developing robust error correction codes is essential. Leading technology companies like Google, IBM, and IonQ are in a competitive race to build practical quantum computers. Each company is pursuing different hardware approaches, from superconducting circuits to trapped ions. This competition is driving rapid progress. A primary goal for these companies is increasing qubit counts. More qubits mean the potential to tackle more complex problems. Reaching a state known as quantum advantage or quantum supremacy requires a sufficient number of high-quality qubits. Equally important is improving coherence times. Longer coherence times mean qubits can maintain their quantum state for longer periods. This allows for deeper quantum circuits and more complex algorithms to be executed before errors accumulate. Despite the challenges, specific applications are already beginning to emerge where quantum computers show promise. These are often areas where classical computation struggles to provide efficient solutions. The focus is on problems that leverage quantum properties. One significant area of advancement is in drug discovery via quantum simulations. Simulating the behavior of molecules at the quantum level is incredibly computationally intensive for classical computers. Quantum computers offer a potential path to more accurate simulations. This allows for modeling molecular interactions with unprecedented accuracy. Understanding how molecules bind and react is fundamental to designing new drugs and therapies. Quantum simulation could dramatically accelerate this process. Advancements are also being seen in materials science. Designing new materials with tailored properties requires understanding their electronic structure and interactions. Quantum computing can provide insights that are currently out of reach. This could lead to the discovery of materials with novel properties, such as high-temperature superconductors or more efficient catalysts. The ability to simulate and predict material behavior could transform industries from energy to manufacturing. Another area of significant potential, though also a concern, is the ability of quantum computers to break existing encryption algorithms. Algorithms like RSA, which secure much of our online communication, are vulnerable to quantum attacks. This potential threat necessitates the development of quantum-resistant cryptography. Researchers are actively working on new cryptographic algorithms that are believed to be secure even against powerful quantum computers. This is a critical area of research for future security. Nvidia is widely recognized as a leading player in the GPU market, powering everything from gaming to artificial intelligence and high-performance computing. Their hardware has become essential for many computationally intensive tasks. They are a giant in classical computing. However, Nvidia has also taken a significant and strategic stance in the quantum arena. While not building quantum processors themselves, they are positioning themselves as a crucial enabler of quantum computing research and development. Their role is complementary. Traditionally, Nvidia's focus has been squarely on classical computing, particularly parallel processing with GPUs. Their success has been built on accelerating classical workloads. This background provides a strong foundation for their quantum efforts. Now, Nvidia is investing heavily in quantum computing infrastructure, specifically in the software and simulation layers. They recognize that the development and utilization of quantum computers require sophisticated classical resources. They are building the bridge. They are developing software solutions specifically designed for quantum computing researchers and developers. These tools help in simulating quantum circuits, developing quantum algorithms, and integrating quantum resources into existing workflows. While not building the quantum hardware itself, they are also developing hardware solutions that are essential for interacting with and controlling quantum processors. This includes high-performance classical computing resources needed for quantum control and error correction. Nvidia's strategy aims to integrate quantum processors with classical computers. They envision a future where quantum processing units work alongside classical CPUs and GPUs. This hybrid approach is seen as the most likely path to early quantum applications. They are actively creating a hybrid computing approach. This involves developing the software and hardware interfaces that allow classical computers to send tasks to quantum processors and process the results. It's about making quantum resources accessible and usable. This hybrid model leverages the strengths of both classical and quantum systems. Classical computers excel at many tasks, while quantum computers offer unique capabilities for specific problems. Combining them allows for tackling complex challenges more effectively. A key development from Nvidia is the Qquantum software library. This library is designed to accelerate quantum simulations on GPUs. Simulating quantum systems on classical hardware is essential for algorithm development and testing before running on actual quantum hardware. Qquantum allows researchers to simulate larger and more complex quantum circuits than previously possible on classical computers. This significantly speeds up the development and validation of quantum algorithms. It lowers the barrier to entry for quantum research. Nvidia is also forming strategic partnerships with various quantum hardware manufacturers. These collaborations ensure that Nvidia's software and classical hardware are compatible with different types of quantum processors. It fosters an ecosystem. This move by Nvidia signals their clear recognition of quantum computing's transformative potential. They see it not as a distant threat, but as an emerging technology that will require their expertise and infrastructure to flourish. Their investment and development efforts demonstrate a strong commitment to shaping the future of computation. By providing essential tools and infrastructure, Nvidia is positioning itself as a critical player in the quantum era, even without building the qubits themselves. It's important to understand that widespread real-world applications of quantum computing are still some years away. The technology is powerful, but remains in its nascent stages. It's not yet a plug-and-play solution for most problems. The technology is currently in its early stages of development. We are still in the era of noisy, intermediate-scale quantum computers. These machines are experimental and challenging to work with. Quantum computing faces significant challenges in scalability. Building quantum computers with a large number of high-quality, interconnected qubits is a major hurdle. Current systems are limited in size and connectivity. Error correction remains a critical challenge. The fragility of qubits means that errors are frequent. Implementing fault-tolerant quantum computation requires a massive overhead in qubits, which is currently impractical. The cost of building and maintaining quantum computers is also extremely high. These systems require specialized environments, often at cryogenic temperatures, and complex control electronics. Accessibility is limited. Despite these challenges, experts predict that early applications will begin to emerge within the next 5-10 years. These initial applications are likely to be in specific, high-value areas where even a small quantum advantage can be significant. Early applications are expected particularly in specialized areas. These are problems that are intractable for classical computers, but might be solvable with near-term quantum devices, even with their limitations. These specialized areas include drug discovery, materials science, and optimization problems. These fields often involve simulating complex systems or searching vast solution spaces, tasks where quantum algorithms show theoretical promise. The development of hybrid systems, like those being facilitated by companies such as Nvidia, may accelerate this timeline. By offloading specific, difficult parts of a computation to a quantum processor while the rest runs classically, we might see useful applications sooner. However, the full potential of quantum computing is likely to unfold over the next few decades. Achieving fault-tolerant quantum computation and building large-scale quantum computers will take time and continued innovation. When fully realized, quantum computing promises to reshape industries across the board. Its ability to solve currently intractable problems will open up new possibilities in research, development, and technology. Ultimately, quantum computing has the potential to fundamentally alter our understanding of the world. By enabling simulations and analyses currently impossible, it could unlock new scientific discoveries and technological advancements that we can only imagine today. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.